can start talking about one-dimensional motion. One-dimensional motion is pretty easy. We like it. Today is the 19th, 2017. And one-dimensional motion is what you were looking at yesterday. Actually, one of them was two-dimensional motion, but we only looked at it in one dimension. So let me ask you this. Look carefully at your desk. Is it moving? Anybody reporting any motion? It depends. Depends on your frame of reference. If your frame of reference is the floor and the walls and the room around us, no, your desk is not moving. If your frame of reference is the sun, is your desk moving? Yes. If your frame of reference is something outside of this, you can think about a person on a bus. There's my bus, it's very fancy. Sitting still. Are they moving? Well, it depends. Is the frame of reference the seat on the bus, or is the frame of reference the road under them? So motion is always relative to some frame of reference. For us, our most common frame of reference is the earth. So we tend to talk about motion in reference to the earth. It's the biggest frame of reference adjacent to us. And we can talk about motion in up to 3 dimensions. We don't want to talk about motion in 3 dimensions. If you're going on to an engineering program, you will talk about motion in 3 dimensions, and woe betide you. The motion that we look at, we tend to pin to a coordinate system, and we use the Cartesian coordinate system. It's easy, and if you want to do the dance with me, those of you who suffered through chemistry, remember the X, the Y, the Z. You can do that dance at homecoming, if you would like. You can do it as a new chemistry/physics line dance, because it also describes the axes on which p orbitals can exist, the X, the Y, the Z. Those are the 3 axes that motion can be pegged to. We're going to start off with one at a time. In Chapter 3, we'll move to 2-dimensional motion. We'll work on 2 axes. We will never work on 3 axes. You don't want to go there. 2's enough for us for now. Plenty. Okay, why can't I pause? Okay, so when we talk about one-dimensional motion, we can talk about the X or the Y. We're going to start off with the X. It's easy. And you can think about a train on a track. It can go forward, it can go backward. It doesn't go side to side. All motion is simply one dimension, front and back. And what we look at is actually not the distance that something travels, but its displacement, which is just the difference in its initial and final position. So if we have an object that starts, if this is our 0, 1, 2, 3, 4, 5, 6, 7, 8. If we have an object that starts here and ends here, so we have an X initial and an X final, and those should be lowercase. Then the difference between 8 and 1, or 7 units, we don't know what these units are. They could be meters, they could be ducks, they could be kilometers, they could be centimeters, they could be, rabid chipmunks. I don't know what the units are here. They're not marked. But the displacement is the difference in the final and initial position. And we always have to look at just those 2 numbers, because that is significantly different than the distance traveled. Okay? Distance traveled can be all over the place, like from here to here, and in the meantime, you go all over the place. Nobody reads Family Circus anymore. It's really stupid. It really is. But they used to always have great cartoons about Billy the little kid, and it would show like all his tracks across the backyard, and through somebody's dog door, and up into somebody's tree house, and over the fence, and into his dog house, and blah, 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 blah. Distance is the number of steps you take. It's the numbers on your odometer in your car. Displacement is the distance between where you started and where you ended, the difference between your initial and final position. So let me ask you this. If you wake up in your own bed in the morning, what is your 24-hour displacement? 0. Once again, I got nowhere. Yes. If you wake up in your own bed, your 24-hour displacement is 0. You could go all kinds of places in that 24 hours. You could drive over half of Ohio in 24 hours. You wake up back in your own bed, right where you started the day at, your displacement is 0. So it's an important concept. Doesn't matter if you take 2 different routes to get back to where you went. It doesn't matter where you go. It doesn't matter if you go to the North Pole and back. If there is 0 difference between your initial and final position for the time period that we're looking at, your displacement is 0. Okay? Distance is absolute. There's no positive or negative. Because if I go from here and back and forth and back and forth and back and forth and back and forth because you keep forgetting things, that number doesn't change despite the fact that really when I end up right back here, I didn't get anywhere. Displacement can be positive or negative because if we look at this track, if we're assuming that there are the negative numbers here, we have assigned one direction as positive and one direction as negative. We tend to default to the Cartesian coordinate system. So those of you who know me know that I can't do left and right. But this is my right hand. Positive axis, I guess, is the right. Right and left don't make sense to me. Negative axis is the other side. You know your Cartesian coordinate system. Positive, negative. And we just kind of assign that. We impose a Cartesian coordinate system on the world. It's not really there. If we impose that Cartesian coordinate system on the world and we say, and I am, for the purposes of illustration, really fudging all the wrinkles in the world, if we say that Route 7 is a straight north-south road, and we know it's anything but, especially right around this little loop, and we say that BLHS, we could even say the old high school site, Beaverdome 1, is the 0 mark. It is origin. And we say that north is the positive direction and south is the negative direction. We are imposing the Cartesian coordinate system on the world, which means that if you traveled from here, if your x initial was here and your x final was here, what would your displacement be? This is 0. 1, 2, 3, 4, 5. What's your displacement? Final minus initial. -5. Delta x equals -5. And I didn't tell you what the units were. Let's say these are meters. Okay. So you've actually traveled a negative distance. Does that mean you didn't go anyplace? No, it just means you went in a negative direction. So we're imposing that Cartesian coordinate system on the world and then treating all our numbers accordingly. Now, how fast did you get there? Velocity. This is a term we use to describe rate of motion. And the average velocity, which we typically show as v sub a, is displacement divided by the time interval in which the motion took place. Our most common units for the time interval are seconds. Our most common units for the displacement are meters. So we typically look at meters per second, and we can do the dimensional analysis on this. If velocity is given in meters per second, and we're looking at meters over seconds, that works. Meters per second equals meters per second. We can also, and this starts to look a lot like a slope equation. That's a bit of foreshadowing. It's equal to our, well, it's equal to our final position minus our initial position divided by our final time minus our initial time. Change in x over change in t. Change in x over change in t. Sub A is important. There will be points when we'll kind of fudge that when we're talking about constant motion, and we'll just start calling it v. Just fair warning. Now, a little bit of clarification. Velocity is what's called a vector. The vector is the direction that you're heading. Okay? The magnitude is the number attached to it. The vector is the direction in which you are heading. It's what we call a vector quantity. So saying your velocity is 10 meters per second, it's not true. It doesn't make sense. Your velocity can be 10 meters per second to the west or 10 meters per second to the south. Or 10 meters per second in the negative direction. We can use sign as a proxy for direction. We do that sometimes. Speed is all about magnitude. It's a scalar quantity. So we have vector quantities and scalar quantities. We'll talk more about those in the next chapter. So you can have two objects that have the same speed but different velocities because they're heading in different directions. If you would be, oh, and I should mention, this is probably the first thing that you want to put on your note card. It's sort of the root of all of the other things that we're going to work with. V average equals delta x over delta t. You can also just write V equals delta x over delta t, but it's a good starting point for your note card. I sometimes forget to put this one on my note card because it's the most basic of them, so I kind of just automatically remember it. But it's nice as we go further. I find that you guys have an easier time if I remind you to put it on there because it's so obvious you forget it. Okay, so we're going to start off with a sample problem. If you look at page 44 in the book, we're going to do sample problem 2A together, and then you will have a few minutes to work on the 2A practice problems. So, during a race on level ground, Andra runs with an average velocity of 6.02 meters to the east. What distance does she cover in 137 seconds? Well, we know that V sub A equals delta x over delta t. Here's a habit I want you to get in, okay? I'm really serious about this. You're going to think I'm like some sort of physics Nazi. Maybe I am. Write the base equation. List your darn variables. This is so easy, a drunken chimpanzee who's had Algebra 1 could do it. I'm aware of that. It will get harder. And what I want you to do is build good habits while it's really stinking easy, while you could do this in your sleep at 2 in the morning. Because when it's hard is not the time to try to go back and fix the bad habits that you built when it was easy. So I'm always going to list my equation. I am given V sub A. I'm given delta t, 6.02 meters per second east. I'm given delta t of 137 seconds. And delta x is the thing I'm looking for. Putting that list of variables and sticking a little question mark in, I know, it's insulting at this level. I get it. But it's not going to be this easy for much longer. So, now I want to rearrange for delta x. You also absolutely 100% must, because yes, I am the physics Nazi, fa-cha, fa-cha, with the physics whip. In chemistry it's a stick, in physics it's a whip. Show your rearrangement. Show your solution. Don't plug numbers into that. Do not do it. Really, seriously, don't do it. So, V sub A times delta t equals delta x. That's going to become really important because as we move on, you'll start doing a lot of things where you solve two equations and do substitutions a la Algebra 2. So now I can plug everything in, and I have 6.02 meters per second east times 137 seconds equals delta x. So I get a raw answer of 824.74 meters equals delta x. Let's just do a quick dimensional analysis check. I'm going to shrink. Actually, I'm just going to get rid of that now, just to make sure. And yes, again, I realize a drunken monkey could do the arrangement here. I know that I'm doing displacement, so I know, gee, I ought to end up in meters per, yeah, meters per second. Nice, Moser. But let's just check. So I've got meters per second times seconds. What does that equal? It equals meters. Okay, so it's just that little double check. I know this is insulting to your intelligence. I get it, but it's going to get harder. So, how many sig figs can I have? Hold up fingers. 3. I'm limited by the fact that everything here has 3 sig figs, so 3 is the maximum number I can have. So my correct answer is going to be 825 meters. Please circle it. I'm going to tell you at the outset, these are really the first calculations we've done from your book. The textbook's sig figs are often terrible. And when we get into more complicated problems and they give you an answer, very often the sig figs in their answer are wrong or their rounding is wrong. So, you know, we argue with the book all the time. It doesn't do any good. It just lays there laughing. You're assigned all the problems on page 44. So I'll give you, let's see, you've got what? 20 minutes, which is like 5 minutes per problem. I'm going to give you 15 minutes, and then I want to talk about one more thing. So I'm going to give you 15 minutes to do those problems, and then we'll come back. So assigned all 2A problems, page 44. So we can plot velocity. We can find velocity by plotting position against time. Time position graph. What's on the x-axis? What is it? Here's how you remember that. Time is independent of you. Time doesn't care what you're doing. Time marches on. Time does not look left or right. Time just keeps marching. Time is generally your x-axis for that reason. So if, whoops, I am on the eraser. Didn't want to be there. If time is here and position is here, what's average velocity? Well, VA is delta x, change in position. I'm going to write that change in position, over change in time. Well, gee, that's actually rise over run. The slope of a position time graph gives you the average velocity for an interval. Okay? This should be of use to you in doing your lab, where I believe you are graphing some data about moving objects. Huh. Funny that. That's useful. Now, here's the catch. Velocity isn't always constant. So when we have something moving with changing velocity, the line of best fit on a position time graph is going to be curved because the velocity is changing, so the slope is changing. So you can look at any set of data points for a moving object and say to yourself, well, was the velocity changing? If so, then the line of best fit is going to be curved. Well, was the velocity constant? Okay, then the line of best fit should be straight. Now, will your data be perfect? Probably not. But that underlying guidance should allow you to do a better line of best fit. How many, I know we have, this is actually, I think, the year where I have the smallest number in calculus. Who's in calculus? Okay. This is a small percentage. I've had years where like one person wasn't in. That's fine. It's fine. But what I'm going to say, if you're not in calc, you may have encountered this, but if you're in calc, you have or you will. Have you done first derivatives yet? Or are you still doing limits? Okay. The velocity is also, first derivative is the slope of a point. You can't find the overall slope of that line. The slope changes. You could find the slope of a point if you take the first derivative. You can get the slope of a tangent to a point, but we tend to not look at slope for that curved line, okay? Because we're not doing calc-based physics, we're doing algebra-based physics. So you can find the instantaneous velocity, which is the velocity at a given point, but you can't find the average for an object with changing velocity. Or you can, but it's not all that meaningful. If you've been in a car, have you been in a car? Okay, you're going to have homework if you have not been in a car. What in the car gives you the instantaneous velocity? Speedometer. Yeah, it's the little thing with the little needle that goes back and forth, and it says you're doing 20, you're doing 30, you're doing 40, you're doing 50, you're doing 60, and hopefully you guys would top out there, because anything over that on our roads is unreasonable and not safe. That's your instantaneous velocity. Is there anything in the car that gives you average velocity? It depends on the car. Probably not. In most cars there isn't. Some of the newer cars where you have a trip odometer will give you an average velocity for a trip. I think my mom's car does that. Hers is much newer than mine. So it can be done. But commonly, we don't worry about average velocity for a trip, except when we say, yeah, I drove to Cleveland. It took me an hour and 15 minutes to get to the east side. Oh, you made pretty good time. Okay. And you're not going to calculate your average velocity for the trip, but we tend to think in terms of average velocity when we're talking about trips, but we tend to look in the car at instantaneous velocity. Okay. That's where we'll leave it. And tomorrow we'll pick up with more problems.